Hello, dear students. This is Olga Savina, and this is our laboratory experiment 17B and 18A, Computational Chemistry. First, we will do 17B, cyclohexane chair and bond conformations. We will build our molecules in Spartan and explore their properties. I will follow the procedure given in our laboratory manual. First of all, we have to construct the molecule of propane. I will do it. I'm in a builder mode. It is my new molecule. I will pick up sp3 hybridized carbons. I have to have 3 of them, connect them, and then minimize using energy button. Minimize it. And now I have to measure the bond length and angles. So to measure the bond length between atoms, I have to go to geometry, click on measure distance, and pick up atoms. So the distance between this hydrogen and carbon is 1.095 angstroms. Let's pick up carbon and carbon, and it's going to be 1.519 angstroms. Measure the distance between these two, carbon and hydrogen. It's going to be again 1.096 angstroms. My next step is to construct a cyclohexane chair and minimize it. I will do it. Cyclohexane chair. I will do it using the model kit that is given to me, clicking on rings and then picking up cyclohexane. Okay, here's my molecule, and I will minimize it again using the energy button in the lower right corner. Here's my chair. And again, I have to measure the distances between hydrogens and carbons in this molecule. So the bond length between carbon and hydrogen. Okay, energy, geometry, this and this. Record the result, 1.097 angstroms, carbon and hydrogen, then carbon and carbon, carbon and carbon 1.526 angstroms. You can pick up any other carbons, let's say this and this, the same value. So we're done with distances. Now we have to measure the bond angles. So I have to measure the angle. I'll pick up this, this, and this. And it is 111.64 degrees. Let me measure this. That's again the same. It might be this one. I got the same values for all of them. My next goal is to rotate the molecule so that we can view it end on, like in the Newman projection, and determine whether some hydrogen staggered or eclipsed. Okay, let me do that. This is my chair, and now I rotate it like that. This is my Newman projection from a different point of view. So you have to determine whether they staggered or eclipsed. And then I have to measure the distances between different hydrogens and determine whether steric strain exists, which means if they closer than 2.4 angstroms. So let's do that. Let me do that. Let's measure distance between these two. Sorry, I have to go to geometry again. Geometry and measure distance. Distance between, let's say, these two. It is 2.452 angstroms between these two, to the same value. Let's do this between these two, 3.057. This distance will be too large for, of course, and maybe what else I have to pick up? I'll pick up some adjacent the carbons. I think I measured that. Maybe this too. Yeah, the same value. This is 2. And so on. So I'm done with this part, I think. Yeah. Yes, I think so. So now my goal is to construct a cyclohexane boat. It's going to be my new build, and I will construct it from cyclohexane. I will construct a boat using the following procedure. I will construct it. First, it is my cyclohexane chair. I will minimize this molecule, and then I will add 2 sp3 hybridized carbons to the 4 carbon, and then I will connect this one with the first one. And then I will minimize it, and I will find a boat, and I will delete unneeded carbons. This and this. Perfect. This is my boat. What I have to do with this boat, I don't have to minimize it first, right? If I minimize it, it will be a twisted boat. I don't need it. I need a boat. And I have to repeat the same measurements with the bond length and bond angles. And I have to explore peak 1, peak 2, and both corner. So let's consider this one is peak 1. And so I will determine the distances. So hydrogen and carbon, it is 1.096. Carbon and carbon. Carbon and carbon, it is 1.538. And then finally angle. Carbon, 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 it is 108.65. Now explore another corner. Pick 1, pick 2, second peak. So geometry distance, this and this, 1.096. And then distance between these 2 carbons, it's the same, 1.538 angstroms. And finally, the angle. Yep, 108.65 degrees. Now I have to explore corners and do the same, measure distances between hydrogens and carbons. This distance is 1.097 angstroms. The distance between carbon and carbon, carbon and carbon is 1.535 angstroms. And finally, the angle going to be 110.28. So done. What is my next step? I have to rotate again this molecule and see whether my hydrogen staggered or eclipsed. It's a Newman projection, and we see it clearly what's going on. We'll look at different angle. This is how it looks like. And so you have to make a conclusion if this molecule is stable or not, but it's not enough information yet. We have to measure the distances between hydrogens to determine the steric strain, if it exists. I'm interested in these flag pole hydrogens. Let's measure this distance first. Okay. 1.824 angstroms. Now let's measure these distances between side axial and side equatorial. So this one and this one, 2.276. Too close. These two probably is going to be the same. Let's measure between this and this. 2.877. Far apart, it's obviously seen. Anyway, it should be the same. 2.5, we got the value of 2.5. The corners should be, they are too close on the corners. 2.276. So I think we're done with this part. Now we have to construct cycler. Oh, we have to twist it. We have to twist it. This is my board. And we have to minimize it. We have to minimize it to determine, to find the molecule, to build a molecule of a twisted board, right? So let me start it over to say we can construct it. We can construct it again. Let me do that again. Twisted board, rings, cyclohexane again, and I will do that again. I will do that again, minimize. Doing what I'm doing right now, I'm constructing my board again. Then I have to, when I minimize it, I will get my twisted board. And I have to repeat all measurements for the twisted board. You see it's twisted. Now I'm looking at Newman projection. Okay, let's start it over. This one is going to be our peak one. And I'll measure distances between hydrogen and carbon. It is the same value, 1.987. And between this carbon and carbon, 1.530 angstroms. And finally, the angle. It is 111.87. Now I will do the same with the peak number 2. I will start with the angle. It's going to be the same. And then I'll measure distances. Hydrogen and carbon, 1.097. And then finally, carbon and carbon, 1.523 angstroms. Now I'll have to check my corner. So I will measure the distances between hydrogen and carbon. That's hydrogen and carbon, it's the same, 1.097. And between carbon and carbon, it is 1.530 angstroms. And finally, the angle. Angle. 1, 2, 3. This is my angle. Perfect. 113.60 angstroms. So record these numbers. And so you will be able to compare the molecules of propane, cyclohexane, and in chair conformation, and in board, and a twisted board. And now I have to again rotate it and find a Newman projection and determine if my hydrogens are staggered. And you see it's twisted. It's twisted. But you can make a conclusion. And then we have to measure distances between different hydrogens to determine if steric strain exists. My previously flagged pole hydrogens are, the distance is 2.687 between these two. And now I will measure the distances between axial and between equatorial hydrogens. Let's pick up these two. It is 2.331. These two, the same, 2.310 angstroms. And let's do this. These are 2.653 axial and equatorial, pretty far apart. Okay, so I think I'm done. Now, yeah, you will make a conclusion in your report. Now I'd like to work on experiment 18A, and its first part, it's about isomers, and we have to construct 3 different molecules. First one is cis-2-butene, second one trans-2-butene, and 1-butene. And then we have to calculate their heats of formation, their energies, and compare these energies. I'm in a new page, and I will pick up sp2 hybridized carbon and another one, and I will add sp3 hybridized, and I'm building cis isomer, and I will minimize this molecule. And now I have to calculate the energy. What we will do here, we will go to setup, click on calculations, and we will pick up energy, and we don't have over here AM1 method, we have PM3, we will use this method. And we will determine the energy of this molecule on a display. Have to click on output, and the value of energy is given to us. It is negative 8.3050 kilojoules per mole. This is the heat of formation of this molecule according to this method of calculations. Okay. So now I have to construct the molecule of trans-2-butene, minimize it, and again do my calculations. Set up calculations, and I will pick up the same parameters. So it's ready to check it. It is negative 13.8529 kilojoules per mole. Record this number. Okay, now the last one, it is 1-butene. Here it is. I will minimize this molecule, and again submit it to calculations. It's done. Display output, and this is the value, 8.8221 kilojoules per mole. So now I have to do part B. I have to compare acetone and its enol. I will construct a molecule of acetone this way, and I will replace this by oxygen with a double bond. Perfect. I have to minimize it. Now, again, I have to submit it to calculations. So, and check the energy. It is negative 219.9173 kilojoules per mole. Record this number. And finally, I have to construct the enol. And replace this hydrogen by OH group. Yeah, so now I have to minimize it and check whether the molecule is correct. Let me do it again. Yeah, it looks nice. And now we have to figure out the energy of this molecule. Same things. It is negative 163.5712. So you can compare these two. And now this is the part C. I have to compare two carbon cations, primary and tertiary, and determine which one is more stable, which one determines the major product in the Markovnikov reaction. So we have to construct 2-methylpropane, and I will follow the procedure that is given to us in the lab manual. So it says I have to construct this molecule, and I have to construct it, and then I have to delete unneeded hydrogens. So I will construct primary carb cation. So I have to delete one hydrogen from here. Here it is. So I've deleted it is primary, and now I have to minimize it, and I have to submit this molecule to calculations. I forgot to assign charge because it is cation +1 charge. That's perfect. Done. Now I have to check the value of energy. So it's going to be 908.2436 kilojoules per mole. Record this number. And I will build a tertiary carbon cation right now, again, using a template. And I will delete this hydrogen. This one. This is my tertiary. I will minimize it. And then submit it to calculations. Charge is positive. Waiting. Display. It is 771.1887 kilojoules per mole. Perfect. Let me check if I did everything correctly. And yes, it seems like that. And here I did some modifications. I minimized all constructed molecules and measured their energy. In your template, it says that you have to first measure the energy of unminimized molecules and then measure energy of minimized. But I followed the laboratory manual, and you can consider it as a modification for this laboratory experiment, and you can modify the template that is given to you. Okay, guys, thank you for watching, and good luck.